Last time we talked about, we finished off a couple little like final topics from LQR. In particular, we talked about controllability, right? Which is kind of this other concept aside from the sort of positive definiteness stuff about the cost function. This is a property that the system dynamics have to have, right? Such that you can actually have a feasible LQR problem. That's kind of the other thing you need. Talk through that a little bit. And then we dug into dynamic programming, right? And talked about stuff like value function, cost to go function stuff, Bellman recursion, which ends up being, in the special case of LQR, the Riccati equation. So we saw sort of LQR yet another way. So I guess we're at LQR 4 different ways now. But it's good for you. It's all good stuff. So dynamic programming, really, really cool, really deep stuff. That's sort of, yeah, like one of the other central concepts in this field, right? Cool. And then at the very end, I teased kind of what the Lagrange multipliers are, right? So remember, it ends up being that the Lagrange multiplier is associated with the dynamics in the QP and or in sort of the co-states when you go backwards in Pontryagin. Those things end up being the gradients of the value function or cost to go function and when you do dynamic programming. And actually that holds up in general. That's not just an LQR or linear thing. That holds in general for nonlinear systems. So if you go do nonlinear trajectory optimization and you solve it with like sequential quadratic programming or whatever, like we're going to do later, turns out those Lagrange multipliers at convergence are the gradients of the cost to go. So that's kind of cool and kind of a deep connection between all these ideas too. Okay, cool. So any questions on any of that stuff from before? Everyone feeling good about it? All right, good. All right, so today we're gonna kind of keep trucking and start some new stuff. We're gonna get into convex model predictive control, which kind of builds on both sets of ideas we've talked about. It builds actually on both the sort of QP ideas and the LQR ideas, and it builds also on dynamic programming in an interesting way. So this is why we're doing it now. So the first thing we're going to do, though, is talk about sort of some background on convex optimization, just to kind of fill in some gaps, maybe. We talked a little bit about this stuff. So in particular, right, we talked about how for a QP, you need the Hessian to be strictly positive definite for that thing to be strongly convex. There's some other stuff we're going to get into today that's sort of hopefully going to give you a broader concept of what that all means and why we care. And then once we kind of do that, we're going to do the convex MPC thing, which convex MPC is one of the big ideas in control over the last, like, I would say 15 years. This has become like super, super powerful and popular. It's you know, one of the most widely used and I would say practically useful techniques out there right now. Cool. All right. Any questions before we get into it? I'm feeling good. All right, here we go. So first, I guess, why do we care? So like as a brief foray into like what we're doing before we get into all the background mathy stuff, convex model predictive control, which is what we care about ultimately here, because we want to make robots do cool stuff, is the gist is we did LQR. LQR is awesome, but it is not able to reason about constraints on the system, right? It doesn't handle sort of actuator limits. It can't handle like obstacle stuff, safety constraints. It's purely just dynamics and cost function, right? So what convex MPC is trying to do is take LQR. The way to think about it is take LQR and then try to handle constraints in sort of that LQR framework, I think is the right way to think about it. And one thing to say about this is that, you know, sometimes we have very complicated constraints, but a lot of the times they're really simple. Like, for example, actuator limits are usually just the simplest possible constraint. Right? They're just like scalar bounds on the elements of U. So often the constraints that we need to deal with are really, really simple ones. And then, so if we think about that, we did the Riccati thing and we saw how Riccati is actually this like back substitution solution to a QP. Unfortunately, if I add other constraints to the QP, it changes the block structure and I can't do Riccati anymore. So adding these additional constraints sort of breaks the Riccati thing and breaks the LQR solution. So that's a bummer. But we can still solve the QP, right? So even if even if it's no longer a strictly LQR problem, and I can't do Riccati on it, I can still just go straight up solve the QP, which we already did and saw that that works too. So I can add additional, say, linear inequalities, for instance. I get a QP. As long as I can solve the QP fast enough, I can still do it, and it's totally fine. So that's kind of the idea. And then the kind of the meta point here is that, this stuff has gotten particularly popular in the last 10 or 15 years. And this is what's, on all the quadrupeds. It's, landing rockets for SpaceX. It's in a lot of cool stuff. And the real reason for this is that computers have gotten faster. So we can now solve larger QPs at like sort of hundreds of hertz rates, which is what it takes in most applications to really do it. And like even like 20 years ago, the computers weren't fast enough, especially in embedded systems, right, to solve these things fast enough. Now you can solve reasonably sized QPs at like kilohertz rates. So it's, it's become possible to do this. Incidentally, this stuff goes way back. It goes back to the 70s, but back then, obviously the computers weren't as good, and it was mostly used in chemical plant sort of scenarios where the dynamics are really slow, and you only need to solve the QP, say, once every minute, and that was still real time. Okay, any questions about that stuff? All right, so this is the hopefully sort of motivational pitch, and now we're gonna have to do some like some background stuff to know what we're doing. So first thing we're gonna talk about is convexity, this is like one of the central topics in kind of theory of optimization. It's definitely good stuff to know about. So first idea is, what's a convex set? I should say too, I'm going to give you like the simplest, I think, geometric and intuitive versions of these definitions that I think give you a lot of insight. There are other ways to define these things. In most cases, there's like at least 3 or 4 ways to define these things. I'm going to give you like the geometric definition because I think it's intuitive, but there's also like algebraic ways to define these things that you'll see out there. So first thing, can anyone tell me what a convex set is? Yeah, in any way you want. That's right. Yeah. So who's heard of this before? Hands? Like a quarter-ish? Okay, so a convex set is a set, and I mean this in the mathematical sense, right? So just think about a shape. If we're in 2D, it's a shape in the plane. If we're in 3D, right, something with volume. And the idea is if I take any 2 points in the set, I can pick any 2 points in the set and I connect them by a straight line, the entire line has to be contained in the set. So this guy, for instance, like an ellipsoid, is a crappy ellipsoid because I'm bad at drawing, but like circles, ellipses, boxes, these sorts of things are convex sets, right? So this is convex. If I went and drew, I don't know, some weird bean-shaped thing by contrast, right, like this is not convex because I can pick 2 points, say here and here, and if I connect them by a straight line, it goes outside the set, right? So this is very intuitive, pretty easy. So the sort of geometric definition, which I like personally, is a line connecting any 2 points in the set is fully contained in the set. Okay, cool. And so some standard examples of this. That you will encounter likely are things like linear subspaces. So think like hyperplane, right? So these look like algebraically AX equals B. So we've seen those before, obviously. in QPs, right? So linear subspace, good. Similarly, half spaces or boxes or polytopes, which are linear inequalities. Those look like AX less than equal to B. Those are convex, right? Ellipsoids are another good example that shows up quite a bit and includes spheres as a special case. So those look like X transpose PX less than equal to 1 for a positive definite P. I haven't seen that before. And if P is the identity, then it's a sphere, right? Or if P is a diagonal matrix, it's a sphere. And then if it's not diagonal, or if it's I'm sorry, it's a multiple of the identity, then it's a sphere. And then if you sort of scale it, so it's not an identity matrix, you're basically stretching it out in some axes, right? And then you get an ellipsoid. Okay. And then another one that's very common, that's actually quite useful in a lot of applications, are cones. And these look like, if you have a vector X, the standard definition is you take the first element of X, so like X1, and you say that thing's got to be greater than or equal to the norm of the rest of the vector. So like 2 to n, let's say. And this is a 2 norm. You can use other norms and you'll get other cones. This is called the second order cone because it's a 2 norm. This is like the standard intuitive cone you're used to. This is like an ice cream cone, right? But yeah, you can change that norm and it can be any norm, in which case you'll get something else that's not a round cone. Like if you use a 1 norm, you get a cone with like pyramid sides, right? That kind of thing. So you can use other norms, totally illegal, and do other things in here. But this is kind of the normal cone that you're used to hearing about, right? So so-called second order cone. So I mean here, the 2 norm of, if I take a vector X and I pick off the first element, and that's on the left-hand side of the inequality, and then I pick off the rest, so element 2 to the end, and I take the 2 norm of that. Does that make sense? And you can also, by the way, switch the indices on this, and there's more general versions of this where you have like a matrix in there. What this is, though, this is, if you think about it like as, I don't know, if you make X1 like the Z-axis, then this thing is a sort of standing up cone. If I change the indices, right, that's just turning the cone over or whatever. So that's kind of the idea. Make sense? If you think about it, what this is saying is that like X1 has to be above sort of a unit circle. And that gives you the, I don't know, you can draw it. It's not too hard. Yeah.
With that matrix multiplication, that would give you like a sort of a stretch.
Yeah. So you can add a matrix in there, and that's basically letting you rotate the cone, stretch it in certain directions, whatever. So you can do stuff to it. In general, you can have a linear transformation on both sides of that inequality, and it's still some kind of cone. Cool. Okay. But yeah, for us, this is good enough. Like that's the most basic version. Okay. By the way, this shows up in a lot of places. It shows up as thrust cones for landing rockets. That's the natural sort of like actuator constraint for a rocket. It also shows up as friction cones when you're walking. That's cool on friction. So it does show up a lot in applications. Okay. Any question about this? So this is convex sets. The next idea that we got to talk about is a convex function. And the idea here is we're kind of bootstrapping, right? So, and again, this is a geometric definition. There's pretty straightforward algebraic definitions as well, one of which we've kind of already seen with the whole positive definiteness thing. Maybe we can talk about that. But a good geometric definition is a convex function so a function, say f of x, and here we're thinking about an objective function like that we're minimizing or whatever. So it's from Rn to R. So it's a scalar valued function of a vector. So each vector spits out a scalar like an objective function or cost function for us, whose epigraph, and I'll define that in a second, is a convex set. So anyone know what an epigraph is? Everything above the line. Yeah. So if I take if I plot f, let's just for now make it a really simple situation where I can draw it. So it's like a, 2D center or 1D function. So if I plot, let's say f is like a quadratic sort of thing, and it looks like this. The epigraph there, so that's f of x. Let's say f of x equals x squared, something like that. This thing's epigraph is everything above the curve. So it's everything in here. So if, think parabola or whatever, and we do a lot of quadratic functions, right? So think about x squared, it's a bowl, and the epigraph is everything above that. So everything inside the bowl, and that thing intuitively, right, based on our definition of convexity, that thing's convex. I pick any 2 points in the blue region, and it's, the line between them is in there, right? Make sense? And similarly, right, I take some other random weirdo function, and it's wiggly, and draw it, right? And if I do this kind of thing, this guy is not, because I can, if I take the epigraph in here, I can pick 2 points in here, right? For instance, like here, and draw a line that leaves the set. So this is not convex set over here, right? Cool. Do you want to know another definition of a convex function? It's pretty, there's like some algebraic ones. There's a lot of them, yeah. Yeah, that's another good one. It's like a secant condition, right? Another, that's actually almost the same as this one, by the way. That one kind of follows from this one. Another good one that's a more algebraic flavor is if the Hessian second derivative, which is like the curvature, is always positive. That also leads to the condition you just said, right? And that's where the Hessian kind of thing for the QP comes from. And that's called strong convexity. So which is obviously true for like this quadratic bowl and stuff like that, right? Okay, and not true for the second one, right? Because it curves down in some areas. So that's clearly a negative curvature, sort of negative Hessian situation. Okay, any questions about this? This holds in general. So it's a function from R into R. So like think bowl kind of shaped things. But yeah, like if I were to do this in n dimensions, still fine, right? Okay, cool. And so some standard examples that we will sort of encounter would be things like, let's see, linear functions. So this would be like f of x equals c transpose x. That works. Quadratic functions, like we already have seen a bunch. So this would be like, in general, f of x equals something like x transpose qx plus q transpose x with a positive definite q. I guess positive semi-definite, strictly speaking. If it's positive semi-definite, that means it's got, some zero stuff in there. And that's still convex. That's weakly convex. Strongly convex means it's strictly positive definite. And then other ones that are very common are norms. So like, actually all norms are convex, which is a fun fact. So 1 norm, 2 norm, infinity norm, any norm you like, they're all convex. Okay, so far so good. So we got convex set and convex function. Everyone good with those? Okay, so now we can define what a convex optimization problem is. So a convex optimization problem means you are minimizing a convex function over a convex set. Said another way, it means the objective function is convex, and then all the constraints represent convex sets. So we've got, for example, linear, quadratic, or norm stuff in the objective function, and then the constraints look like some of these things. And you can have combinations of these, right? You can put these together in various ways, but that's it, right? So constraints look like these convex sets. Objective function looks like these convex functions. If that's the situation, then you have a convex optimization problem. So some standard examples of convex optimization problems that you will likely see that we're going to, see in here. which are literally just different combinations of the things we just wrote down in the costs and constraints, would be linear programs. By the way, program in this context means optimization problem. That's an old word for programming, is an old math word for optimization. So I don't know, you'll see that around. So these all have abbreviations for short. So linear program is an LP. That means f of x is linear. And the constraints c of x are both linear. Sort of makes sense. Quadratic programs, which you've already seen. These are called QPs, as we already know. And this is quadratic f and linear c of x, the constraints. Next, there's sort of a hierarchy of these things that people talk about. So QP is quadratic f, linear c. The next one is kind of quadratically constrained quadratic programs, which you can guess what that means. These are abbreviated QCQP. And this is a quadratic f and then quadratic c of x, which geometrically means ellipsoid. Okay, the next one is a second order cone program, which is what it sounds like. It's an optimization problem with a constraint set as a second order cone. And these actually do show up quite a bit. These are like kind of popular. This is an SOCP. And these actually have a linear f and then cone constraint. Anyone know why we sort of went to a linear cost function here as opposed to a quadratic cost function in the standard definition? Want to have a guess? So it turns out I can transform. So there, I mentioned there's like a hierarchy situation here. Turns out I can transform any convex QCQP into an SOCP. I can transform any convex QP into a QCQP into an SOCP. You get the idea. And the trick is I can introduce a slack variable that upper bounds the quadratic cost function, and I can put that in as a constraint. And I can turn a quadratic cost basically into a second order cone constraint. And then I can have a slack variable that upper bounds that thing that I put in the cost function. So now it's a linear cost. So I can sort of transform quadratic costs into linear costs with quadratic constraints and make a QP into an SOCP if I want to. So I guess basically the story is you do not need quadratic cost functions because they're sort of already handleable in there by sort of change of variables tricks. Okay, so these things show up quite a bit. In particular in control, QPs are like super standard, used all over the place. SOCPs are also quite standard, and especially in aerospace applications, because that's how we land rockets, it turns out, because those thrust constraints are conic. So those show up a ton in aerospace applications. Cool. So any questions about this? Okay, so these are what they are. So now the question is like, why do I make such a big deal about this sort of convex story and these specific types of convex problems? So the answer to that is that convex optimization problems don't have spurious local optima that satisfy the KKT conditions. So basically the story is, and you can kind of see this visually from here, right, from this picture, like the thing on the right is non-convex, has lots of wiggles and it has multiple local optima. So if I use a local solver like gradient descent, Newton's method, whatever, I'm going to land in the closest local minimum to my starting point, presumably, and I'm in general not going to get to the global optimum, right? Whereas the thing on the left is a nice bowl, and it only has one minimum, which is the global minimum. So this is kind of a general property of convex optimization problems, that they basically all local minima are global minima. There's some subtlety here, right? Weakly convex, i.e. the semi-definite Hessian case. That means you can have multiple local optima, i.e. and you can have a continuum of local optima. You can have a valley that's flat at the bottom, but they're all equivalent. They all have the same cost, right? Strongly convex which is the strictly positive definite situation. And that means there's only one optimum, and it's the global one. So that's kind of the strong versus weak convexity story. But basically, the big deal here is that there's no spurious local minima that you'll get stuck in if you kind of try to solve this thing. And let's see. And what that means practically is that you can basically to first order. There's some caveats to this. So I don't want to get in trouble, but basically what this means is these problems are, quote, easy to solve. You can always solve them. You can solve them efficiently numerically. And when you solve them, you get an answer. You know it's the global optimum, and you can like certify it and like count on it. So this means like, you can always solve these. So this is really, really what you want if you're doing this online, right? If you're doing this online in real time, you want to be able to bound the runtime. You want to know you're going to get the solution. You never want to have like sketchy situations where you could get stuck or get the wrong answer, right? So that's kind of what's going on here. So these things don't have any spurious local optima that satisfy KKT conditions. So in other words, if you find a solution to the KKT conditions, which is what we've been doing all along with Newton and stuff, then you have the solution. End of story. And then like from a practical standpoint, like all these kind of standard things we just wrote up here, if you just throw Newton's method at it the way we've been talking about, it's basically guaranteed to converge fast and get you the answer, as long as you don't do anything stupid. You can do stupid things still. Like you can, have horribly scaled stuff and ill-conditioned stuff because you wrote down bad cost functions or chose bad units or whatever. But assuming you're somewhat smart about writing your problem down, you can be very confident that Newton's method will converge, and will converge quickly, and that it doesn't matter what your initial guess was, which is a big deal. So it's super reliable. And practically speaking, for like the interior point method kind of stuff that we did, those generally, if you tune them well, you can get those to converge basically in like 5 or 6 iterations to machine precision from any initial starting guess every time, which is awesome. So we'll say like 5 to 10 iterations, kind of thing. Cool. And yeah, so this kind of means you can similarly, like, because I know that, right, I can bound the number of iterations. And then when I write the problem down and I know the problem size, like I know the size of the state vector and all the matrices, I can literally tell you that's like 5 to 10 Newton solves, right? It's 5 to 10 linear system solves. I know exactly how long it takes to solve one of those linear systems. So I can actually bound the solution time, and I can give you hard guarantees on real-time performance. This is a huge deal. Okay, so this is how you get all the guarantees and all that good stuff. Any questions about this? Yeah.
So, if the constraints are convex as well, like there's a ball that you're minimizing and there's an ellipsoid.
Sure. Yeah.
Side.
No, that you want to be inside. You need to be inside the ellipsoid. Being outside the ellipsoid is non-convex, which is actually shows up a lot. That's like obstacle avoidance, right? So if I have like keep out of this circle, that's actually a non-convex. The free space needs to be convex, which actually makes a lot of robotics problems with obstacles hard from this perspective, which is why we need like sample-based planning and search-based planning. All right, so everyone cool with this?
The ball is like this, and we have an ellipsoid kind of dribbling out of the ball. One there union, like there'll be 2 million.
It's a little subtle. So yeah, so you're kind of conflating 2 different things. The bowl is defined over the ellipsoid. So in 2D, think there's a circle, there's a bowl whose cost is like above the circle, right? So I'm minimizing, right? That's kind of the picture. All right. Everyone good? Okay, cool. So this is the convex optimization story. By the way, this is like a very big topic. We spent like half a lecture talking about convexity and convex optimization. There's whole courses in this. The most famous of which is probably Stephen Boyd's convex optimization course, which is online and wrote the book and everything, and it's fantastic. So like if you're into this stuff, I highly, highly recommend taking a convex optimization course. It's really, really good stuff. It's sort of the basis. It's the basic theory of optimization, essentially, right? And it's really good. You should know about this stuff if you're serious about this kind of thing. Highly recommend finding one of those courses either here or online. Go through Stephen Boyd's stuff. It's good stuff. Okay, so now we're going to get into the control stuff. So convex MPC. The idea here is really think about it as constrained LQR. And I think the right way to think about this, which is not necessarily the way you'll always see this talked about, though, is to actually think about this as approximate dynamic programming. That's like the right way to think about it. And so we want to remember the DP setup from last time. Remember, after we did the Bellman thing, we got our cost to go function, our value function. And then when we want it, if we know V of X, and we want to find the control at a given time step, we want to find U, we can solve this one-step minimization problem to get with V and like the one-step cost to get U, right? And that actually defines the policy. So if we have a cost to go function, V of X, we can get U by solving a one-step problem, which looks like this, right? So we've got UK is argmin over U of the one-step cost, L of XU, plus sort of the cost to go for the next time step with the dynamics plugged in. Also known as the action value function or Q function, right? Cool. So, and for LQR, we know exactly what this looks like, right? It looks like I can plug in all the various functions and get like this guy. And then this, I've got my dynamics. And this is that P. Cool. Okay, so I've got that thing. And in principle, I'm solving this thing's a QP. I can add constraints to it if I want to, right? I can add any convex constraints I want to that thing, and I can solve it as with a solver and get an answer. In principle, I can do that, and that's sort of allowed. But sorry, turns out if I just do that naively on this one-step problem, it's going to work really poorly. It's going to suck. It's not going to do well. Why will it be bad? Anyone have any thoughts?
Is it because your V was taking into account your
Exactly, yeah. So V, which is including the entire future, knows nothing about the constraint, right? Okay, so that's annoying. Anyone have any thoughts on how I can make this better? So the sort of obvious thing I can do here is I can just add more time steps to this one-step problem in front of the V. I can add as many of those as I want. It doesn't change the problem at all, right? It's totally legal. If you have the exact V, there's zero reason to do that, right? It's stupid to do it. It's extra work. But it doesn't change the answer. But in this case, where I'm treating V as some approximate cost to go, and I'm like messing with things, adding more time steps to this one set problems may be a good idea. Is kind of the insight. And we'll talk some more about that. So there's no reason I can't just add more time steps here. And something kind of interesting, there's like a really intuitive reason why this is a good idea. So let me write this down. So what we're now talking about is we're going to define some number of time steps we'll call the horizon H, which is less than, the full N of the original problem. So it's looking like, very much like the original problem. And we're sticking to like this LQR sort of setup, right? But in general, you can do other stuff. This is just kind of, we're easing our way into this. So very LQR flavored. And then we're going to put in as the terminal cost of this shorter horizon problem, we're going to make the terminal cost the cost to go. And here, right, it's an LQR cost to go situation. But this, you can do this in general. Okay, so the idea here, and yeah, some no's, right? So this H, which we're assuming here is less than big N, our original horizon, is called the horizon. And if I just solve it like this, I will get the exact same answer as the original LQR thing, right? I didn't change anything about this. And if it's exactly LQR and that's exactly the cost to go and I didn't change anything else, this is exact, doesn't change it. So I can add it, I can make H anything I want. It won't change anything, right? Without the constraints. So that's important to know. This thing, so we call it MCC. I kind of threw that word out there. Another name for this, by the way, now that we have this concept of horizon, is receding horizon control. You might hear exactly matches LQR. For any H. But now I can add constraints to it. And sort of the reason that this makes sense and the reason this is a good idea, let's say I'm solving an LQR problem. The idea here is I want those constraints in there if I get a huge disturbance, right? If I get knocked really hard, then the idea is that like the linear feedback in the LQR is going to, let's think about just actuator limits for now. If I get knocked really hard, I'm really far off. The linear feedback is going to really like rail my actuators. And then if I'm not reasoning about that effectively in the controller, that's going to be bad. I'm going to go unstable and blow up. Cool. So that's the idea. So let's think about it in that concept. Let's think about it as like a giant impulse response situation. So I knock the thing really hard. It's really far off. I'm now going to, be on the rails on my actuators, right? After that first big disturbance. So I'm probably going to hit the constraints. But if the controller's working, it's going to try to steer me back towards the reference. And as soon as I'm like getting back towards the reference, I'm now off the constraint limits. And I should be back in an unconstrained kind of setting where the constraints are inactive. And I'm back to an LQR scenario, right? So the intuition of why this is a good idea is if I give you a really huge disturbance, I'm going to reason about the constraints over, let's say I make H, I don't know, like 5 or 10 time steps. The idea here is that this controller is going to be able to steer you back towards the reference within that first window of 5 or 10 time steps where this thing's explicitly reasoning about the constraints. And then by the end of that horizon, hopefully I'm back off the constraint and I'm back to, and the constraints are inactive, in which case it's just LQR again. So the insight is I want to have a long enough horizon that this thing can fully reason about the constraints until I'm off the constraint by the end of the horizon, in which case it's back to like vanilla LQR, and that cost to go is correct. Does that make sense? So having this extra horizon, extra time steps in front of that cost to go is letting me like get it back to it's letting this thing reason about the constraints until I'm back to an LQR situation, until I'm off the constraint manifold again. Does that make sense to everybody? Cool. So let's write that in. So we're solving this kind of explicit constrained optimization thing. Over the first h time steps. And this should hopefully get the state close enough to the reference. Oops. That the constraints are inactive now. And therefore the LQR cost to go is correct. Like for the rest of the future. Cool. Okay, so this is kind of intuition, and that kind of holds right for these actuator limits. Sort of in general, there's a lot to say about this. So there's sort of, so we sort of wrote this as like assuming LQR plus constraints. We use LQR cost to go, which doesn't reason about constraints. But if we have enough horizon in front of that is reasoning about the constraints, it'll kind of get us back towards the reference enough that the LQR cost to go is kind of right farther into the future. That's a good insight, good intuition, but it's sort of, there's more to say about this, right? Even on a nonlinear problem, when I do nonlinear MPC, I'll still very, very frequently use an LQR cost to go as a terminal cost at the end of the MPC horizon, because it's still kind of getting the flavor of the cost to go for the rest of the horizon. So in general, you can use very, very approximate cost to goes. But there's a trade-off. Essentially, let's see, a good approximation of the true cost to go, right? So remember, right, this is approximate now. Now that I have these constraints, this is not the true cost to go anymore for this problem. It's approximate. The better the approximation, we need some kind of, cost to go at the end of our horizon in the MPC controller for this to work. That idea that you have some kind of approximation of the cost to go as the terminal cost is a key idea in MPC. The better that thing is as an approximation to the true cost to go, the shorter you can make the horizon. Because in the limit, if it is the exact cost to go, then you only need to solve a one-step problem with one time step, and that's exact, right? From the dynamic programming story. But often, writing down, a cost to go is hard, and in general, I can't do it. This is where, a lot of like learning kind of stuff comes in, right? Learning a good value function somehow offline, then I can shove it into my MPC and do this kind of thing with it, right? Okay, so the kind of opposite side of this story is that if I can have a longer horizon, then I am less reliant on V being good. So the longer I make the horizon, the crappier V I can get away with. And there's kind of a tuning game here or a trade-off game. So in the limit, if I make the horizon really long, I can basically solve the whole problem and I don't need any cost to go, right? So there's this kind of trade space in there of like, the better you can make the V, the shorter the horizon can get, and therefore the faster you can solve this thing, presumably. If I can afford to have a longer horizon, then I can get away with a crappier V, and I can use like very, very rough approximations for V. Okay. Any questions about that? Yeah. In practice, yeah. Like in practice, we're approximating all kinds of stuff all over the place, right? And using approximate models and approximate value functions. And in the end, yeah, there's going to have to be some kind of, you're going to do some Monte Carlo stuff in sim. You're going to try it and test it, right? There's a lot of theory that backs this stuff up. And there are, you can prove closed loop stability and convergence of these things under all kinds of assumptions. That said, those assumptions usually break in real life. So it's sort of always, you can have all the guarantees in the world, but like you're going to violate those assumptions in a lot of cases in real life, right? So yes, there's still a lot of tuning and trial and error. That said, there's really, really solid theory here that you can kind of show, modulo assumptions on things that you can give various guarantees here. And yeah, you can actually kind of you can enforce stability and safety in these things in pretty compelling ways, which is the power of this stuff. Yeah. Let's see. Fun fact I'll throw out there. We haven't talked about this too much, which is why I haven't done it. But I mentioned briefly like these Lyapunov stability ideas, which are kind of slightly more general nonlinear versions of stability than we talked about, but maybe we'll talk about it a little later. Turns out you can use a cost to go function or a value function as a Lyapunov function to prove stability in these things, which is kind of cool. Yeah.
That we have, that only holds if like the reference state that we're trying to achieve has constraints inactive.
That's right. Yeah, you're totally right. Yeah. So that story was like it was a little fairy tale story to sort of try to give you some intuition and insight. It's obviously not true in general, right? You can create scenarios where you're like always riding a constraint or something like this, right? The real story is this one, that like what this is really doing is like an approximate dynamic programming thing where V isn't correct. And so you're going to stretch the horizon out in front of it. And like the longer the horizon is, the crappier the V can be. Make sense? In the limit, right, you just solve the whole problem. But what this is trying to do is the idea is that V is at the tail of your short horizon, and it's trying to get you some information about the rest of the problem that you're not including in your short horizon in the MPC, right? All right, cool. So now we're going to go do it. And we're going to do this on a little example. We're finally going to get away from our sliding brick double integrator. We're going to do something a little more fun. And I'm going to actually write down the dynamics for you because I think it's worthwhile for the computer scientists among us who've never written down differential equations to see these things once in a while. No offense. So here's what we're going to do. And we'll come back and do some more of this kind of stuff, some fancier versions of this later in a couple weeks once we learn some more stuff. But we're going to talk about a planar quadrotor. So this is like our first sort of nonlinear, more fun system. We're actually, by the way, we're going to do a full 3D quadrotor in a couple weeks, but we're skipping that for now because I got to teach you about Lie groups and rotations and stuff like that first before we can do that. But so we'll do the planar version for now. So we got weird. We got two propellers. We have like a center of mass situation here with like a body, and then we've got a couple of variables in here. So we've got a mass for this thing and inertia, which in this case is just a scalar because it's and then there's a length in here, so which we're going to make the kind of distance between the props. And then we're going to have some coordinates. So we're going to make it just kind of like X, Y, Y's up, and then a theta for the tilt of this guy. And I'll write down the full nonlinear dynamics. This is like just F equals ma is all I'm doing here. Oh, and right, we got two thrusts. So our controls are the thrusts here. So this is U1 and U2, let's say, for the two propellers. And because it's in 2D, we're not reasoning about torque, prop torque. It's just thrust it's just a force in the up direction. So if I do F equals ma on this guy, I'm going to get in the X direction, mx double dot is equal to minus U1 plus U2 sine theta. This is just me doing trig, right? A little angle math there to get the X component of the thrust. And then in the vertical direction, my double dot, it's U1 plus U2 cos theta. And then there's gravity. So I got minus mg over here too. And then in the theta direction, the tilt angle, I've got J, the moment of inertia, times theta double dot is equal to, and this is just me computing like this is like an R cross F torque calculation. So it's 1/2 L times U2 minus U1. So yeah, this is like freshman physics, F equals ma stuff. Hopefully everyone's cool with that. I'm just giving it to you because we're going to use it and, for your own personal, kind of whatever. And then what we're going to do now is linearize this so we can do LQR stuff with it. And we're going to specifically linearize this about a hover. So at a hover, we're going to have U1 equal to U2, and they're going to have to add up to mg, right? So U1 plus U2 equals mg. So these guys are each on their own going to be 1/2 mg. That's kind of the hover condition. And if I kind of just go plug that back into these nonlinear dynamics and linearize everything, and when I say linearize everything here, it's literally just a small angle approximation. So we're going to have sine theta go to theta and cos theta go to 1. And then, yeah, things are going to simplify down a bunch. We're going to get delta x double dot is approximately minus g delta theta. We're going to have delta y double dot approximately 1 over m delta u1 plus delta u2. And then we're going to have delta theta double dot approximately 1 over j L over 2 delta u2 minus delta u1. Cool. Just small angle stuff. Pretty straightforward. And now what I'm going to do is stack those up and put them into a state space model with an A and a B matrix. So I know this is super simple for some of you guys. I'm just doing this because I know some of you guys have not done this kind of stuff before. So hopefully this is boring and you've seen this before. So here we go. This is x dot, right? So there's the dot stuff. Here's the double dot stuff. So that's x dot. And then we're going to have an A matrix that's going to have a big 0 block over here, and then a big identity block over here, right? So that's just saying the velocities equal to velocities. And I'll write the full state, I guess, here. Delta y, delta theta, delta x dot, delta y dot, delta theta dot. And then this block's 0. And then the lower left block just has that minus g term in it. So it's 0, 0 minus g, and then the rest of this is zeros. So the A matrix is kind of simple. And then the B matrix is kind of where the action is. It's got a big 0 up here, and then down here, it's going to look like the following. So we're going to have some 1 over m's in here for the delta y double dot stuff. And then this bottom block is minus L over J. Is there a 2 in there? Yeah, there should be a 2 in there, right? Minus L over 2J, I believe. Okay, and then this is, delta U1, delta U2. Cool. So this is x dot equals A times x plus B times U. Everyone cool with that? Did I screw anything up? You guys got to keep an eye on me here. You were right. Did I flip that? Oh, yeah, I put a minus on this one. There shouldn't be a minus, right? Okay, all good? Okay, so yeah, so now we have a nice state space model. This is good. And now we're also gonna write down, a cost function for this guy that's gonna be super simple and very much the sort of thing we've been doing. So no surprises. We're gonna have the horizon in here. And we're gonna, some slight tweak that I think I'm gonna explicitly tell you about is we're gonna have a reference in here, right? Remember, we're doing deltas, right? So you can think about it as like x minus x ref. Which doesn't change anything, right? And then delta U, cool. And then we've got our terminal cost, and just to, this is hx, and same thing. We're gonna have a reference x that we're gonna try to track here that's not the origin in particular. That's why I'm belaboring this point, because we're gonna we want it to hover some distance off the ground, right? So x ref is not 0. Okay, cool. So we got some dynamics. We linearized them about a hover. And then we've, the xref is the hover point, right? So it's gonna have 0 velocity, but it's gonna have a non-zero height in there. And we're gonna maybe want to change it at some point. So that's cool. So any question about anything I just did? Everyone feeling good? Okay, so now we're gonna actually pull up some code and have some fun with this. Ooh, my battery is dying. That seems bad. Plug in before we do anything else.
Our state itself is like delta x.
That's right.
But
Yeah.
x reference will be the height we want to reach with respect to like
Yep. So yeah, so I mean, you can write this a couple different ways. You can sort of do the reference stuff like x minus x ref there is delta x. Yeah. I'm just kind of making that a little bit explicit because that's how I wrote it in the code because I'm changing the reference in some spots. Is there a place I can plug in over here? We might have a problem in like 2 minutes if I can't find a plug. All right, well, let's try this. And then if I have to move, can we see an outlet anywhere?
There's one way over there.
Okay, that's a little far. There should be one on this cart. They're usually, oh, here we go. We're in business. Or not. Doesn't stay in the plug. Okay, good enough. Hopefully we've dodged a bullet on that one. Okay, here we go. So this will be up as usual, right? Using a bunch of packages. In particular, we're using a package here called OSQP, which is it's one of the better sort of general purpose QP solvers, and we're going to use it a bunch in the class. It's also super widely used in industry. It's good to know about. It's written in C, but it has bindings to Python, Julia, MATLAB, all the usual things. Has a nice interface, easy to use. You're going to use it on the homework. We use it a lot in the lab. It's kind of our go-to first, prototype choice for QP solvers. And then here's our model stuff. So we've got our, usual things. So we're just making this easy, right? So gravity 0.8, whatever, mass set equal to 1, so 1 kilogram. We made L about 30 centimeters, so yay big. Trying to make this like sort of realistic. And then the inertia there is, I don't know, something that seemed reasonable. And then we're putting thrust limits on this. So I made these sort of like relative to gravity. And yeah, stuff that seems reasonable. And then we're going to do this at 20 hertz, which is sort of fast enough, arbitrary choice. You can play with all this stuff. None of it's sort of, there's nothing special about any of those choices, I guess, is the message. Kind of arbitrary, trying to be reasonable. Then what we got in here? So this is my fully non-linear plane cloud rotor dynamics that we wrote down, just F equals MA stuff. So this is the real deal non-linear stuff. And I'm writing this because we're gonna simulate it on the full nonlinear model, but we're gonna use the linearized stuff in the controller, which is kind of always what you should do, right? Cool. So that's that. We're going to use RK4 to do this, which we already talked about, right? Which is your go-to first thing to try with this kind of thing when you're trying to integrate nonlinear stuff. And then I'm going to get my linearization, my A and B matrix. I wrote them down for you, but I'm going to be lazy and use for diff to get them, which honestly is what you should do too. And we're going to do this in all the homeworks. And in particular, one thing I'm doing here, which you should do too, is I'm calling forward diff not on the continuous dynamics, but on the RK4 dynamics. So I'm calling forward diff on the discrete time dynamics. So these are going to be my discrete time A and B. So this is actually a good idea, by the way. If you're going to do forward diff, just do it through the Runge-Kutta integrator, and like then you got the discrete time stuff right there, and it's exactly what your simulator is doing. So it's a good idea in general. You shouldn't call forward diff on the continuous stuff and then do weird things to get the discrete ones. It's just do this. Cool. So now we should have a discrete time A and B, and I also wrote down cover conditions just to prove to you that there are cover conditions. I plugged them into the dynamics and see it's all zero, right? So x dot equals 0. It's really an equilibrium point. What did I make the hover condition? I just made it all 0. Nothing to use, right? So that's good. What else we got in here? Okay, so this is just kind of setup stuff, right? So we're going to do this for the states, number of actuators. This is just bookkeeping. We're going to do this over a 10-second, like we're going to simulate it for 10 seconds. So the rollouts are going to be 10 seconds. But then in the MPC controller, I'm going to do it over a much shorter horizon. So here's a cost function. Again, just made up, nothing special about this. Go play around with it. Let's see. Okay, so now what we're going to do here to like make this interesting is we're going to use LQR as a baseline. So I'm first going to write down the QR control. This is stuff we've already done, right? So from last time we've got dare discrete operator crowd equation. That's going to give us the P matrix. LQR is K matrix. We've already seen that. So this is infinite horizon LQR, linearized about a hover. And then I'm writing the controller down as a function there that's going to actually do the x minus x ref thing for me. And also plug in the open loop hover, right? So remember, this is a delta U and delta X situation in the LQR, right? Okay, cool. And now what I'm going to do is set up the QP for the MPC controller. So this is the interface for OSP. It's a little minor. I think it's really not that bad, honestly. Most of this is just me building sparse matrices. So this is almost exactly the same thing as we did before when I built the QP for the unconstrained LQR problem. Same exact setup. I'm just adding in some additional constraints. So all this stuff here, these are some like bookkeeping things and I'm product tricks to build the block matrices. So the first one there, I guess I should do this. This is a nice little trick. It's a matrix that picks out. So I'm going to stack up all the variables in kind of the same way we did before, where it's like XU, X1, U1, X2, U2, blah, 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 stacked up in a big vector. So I'm making some like nice, convenient bookkeeping matrices in here that are picking out like things I like. So in particular, this big U is picking out all the U's from that kind of thing. I made a big theta that's going to pick out all the thetas from the state vector for something we'll see later. You get the idea, right? And then the rest of this is just kind of making the big block for the cost, all that good stuff. And then, yeah, you see the big C is the dynamics. So it's AB minus I, like we saw before. All kind of stuff we've seen. Any questions about that stuff? And then what I'm doing right down here, when I actually give the constraints to OSQP, I'm stacking the dynamics constraints and then the U bound constraints, right? That's what's going on in there. Dynamics and thrust limits. I'm enforcing the thrust limits. Okay. And then here, this is kind of just the way the interface works, right? I set up the problem. OSQP has some nice features for actually, it's quite a nice solver for doing MPC because it does warm starting very well. So you call this like setup function and it builds a bunch of matrices and does some factorization stuff. And then online in the loop, you can update only the pieces you need and warm start it really well. That's kind of nice. So this is my MPC controller. Note what I'm doing in here is I'm basically I'm only updating the pieces of the problem that I need to, which are specifically the things having to do with like the delta calculations. So this is yeah, the XREF stuff that we talked about. What else? And then we solve the QP, and then we pick out the first delta U, and then plug it back in and return that. Any questions about that? It's bookkeeping stuff. The interface is actually pretty straightforward. You can like osqp.org. They have really good documentation. You're going to use it on the homework. So hopefully that's all like fairly straightforward. And then this is my kind of closed loop dynamics where I'm simulating this thing forward with RK4. The one extra little nugget in here that I'll like point out is that I'm actually clamping the controls in this loop so that they are clamped to the specified limits, which is what would happen in real life, right? But in particular, LQR doesn't know about this, right? So LQR, when I plug into that thing, it's going to have like whatever linear gain. It's going to spit out controls that are going to violate these limits, and then I'm going to clamp them anyway before I plug them into the dynamics. Make sense? Okay, so that's my closed loop sim. And we're going to start out kind of nice and easy here. So I'm going to set up a reference that's hovering 1 meter off the ground, and then is otherwise all zeros. Make sense? And then I'm going to give some initial conditions here with some error. So I'm going to make it say 1 meter to the right and 1 meter too high. That's what's in here. So those are my initial conditions. And now I'm going to roll this out with both LQR and MPC, and we're going to see what happens. So, and remember what should happen here, if I'm doing something like benign, is they should match exactly, right? So here, what I did was make it a scenario where they weren't hitting the torque limits or the thrust limits, right? So if I don't hit the limits, it's exactly the same as LQR. There's no difference, right? Because I'm not hitting any constraints. So that's kind of what happened here, right? Cool. And also, yeah, we should play with the, got some animations for fun. So this is MeshCat, which is like this little visualizer thing that's kind of fun. And we can sort of animate these things. So that looks benign and cool. Actually, I put this in this other window. It's big. But it's annoying. let's see. So I can try to. This is all annoying and terrible. Sorry. It's a little smaller. Okay, so I can like hopefully get this to work. It's really hard to. Oh, that's still doing that one. Ah, that's super annoying. Okay, never mind. We're gonna ditch this guy. Yeah, I know. That's because I relaunched it. I had that queued up before, but it actually randomizes the port when I like call this thing again. It's annoying. Okay, so there you go. Cool. We can watch it. We're gonna use that in a sec. All right, so that's all benign. That's all expected. What I'm gonna do now is be a little bit mean, and we're gonna start this thing off with a much, much bigger initial error. So let's say I make it, instead of 1 meter to the right, I'm gonna make it like 10 meters to the right. And we're gonna see what happens. So remember this, to put this in context, this looks like a disturbance to the LQR control. This looks like an initial like step response kind of disturbance, right? Okay, so now let's see what happens. Ouch. So LQR is like clearly going off the rails and blowing up, while the MPC thing's actually still stabilizing and kind of doing the right thing. So that's cool. And that's because if we go look at the U's now, it's clearly railing the actuator limits here. And like we said, right, and I'm clamping it in the controller, right? So here, the MPC controller, however, right, it knows about those and it's being clever and it's able to actually explicitly reason about them and still stay stable and do all the right things and still kind of work. So let's go actually watch this because I think it's a little insightful. Hopefully this will work and not be stupid looking. Oh yeah, that one blew up, so that's not of any use to us. Let's see if I can actually, oh, it's over here now. Super annoying. Okay, so let's do that. I'm gonna have to like click fast. I think that one just blew up and looked stupid, so not really worth anything. But this one actually is, there's some insight to have. So this is the MPC controller. So it didn't blow up and go unstable, but what happened? It went through the floor, which is still kind of bad. So anyone know why it went through the floor? Can anyone give me an intuitive explanation for why it went through the floor there? Hmm? No, actually, it's not. That would actually be pretty bad from a cost perspective. So there's another reason.
Did it turn too far, so the linear.
You got it. That's exactly what happened. So we linearized this thing. We did this small angle approximation. And remember, in the x coordinate, I got a sine theta. So it's like a little theta. In the y coordinate, the cos theta just become 1. So what that means is as I tilt, it doesn't know that the linear model doesn't know that the thrust decreases in the vertical axis at all. It thinks it stays constant. So that's the small angle approximation. So I tilt over really far, it's going to fall because the controller doesn't know that it's losing vertical component of thrust in that scenario. Okay, makes sense, everybody? So that's because of linearization error. Any thoughts on what I do to fix that? Could do that. That's a lot more complicated. There's simpler things I can do. Got some idea? Okay, so
We could add constraint that says it has to be above 0.
you absolutely could. Yeah, so the first simplest thing you could do here is put a constraint in there that says, like y component has to be greater than or equal to 0. Totally. That would absolutely be a reasonable thing to do. This is a common thing. This is actually explicitly in the rocket soft landing stuff. You do this because often the low cost solutions go through the ground, which is not what you want to do with your rocket. It turns out there's a slightly better thing to do here in this case, though, that that's the winner. Yeah. So check this out. So I can put constraints on anything I want. This is actually a really big, powerful idea that I really want to like harp on a bit, right? So MPC, I use a linear model, right? But I linearize it about some sort of set point, whatever, in the state space. I can put constraints on the controller to keep me within some reasonable region in the state space where the controllers, where that linearization is good. So this is like one of the most powerful things about doing MPC, actually, that I think is like underappreciated. You can use the constraints to force the controller to stay in a region where the linear model is good. So why don't we try that? Let's see what happens. So I'm going to go back up here. And basically, so the issue, right, is the only thing I'm linearizing in here was the theta stuff, the small angle approximation. So that's easy. I can go back up here where I put all these constraints in, and I can enforce a constraint on theta. So I can say, like, I can just bound theta so that it can't tilt over too far. And then my linearization is going to be good. So here, so this one, we just have the dynamics and the thrust limit. Now I'm going to add a bound constraint on theta to be like, what did I put in here?
So 0.2 radians for sure.
I don't know, pretty reasonable. That's going to have like a relatively small error. Which is, I should also mention, that's like still tilted over pretty far, right? Oh yeah, thanks. Sorry. I can't actually see this from over here. It's very annoying. If I keep moving the podium. So let's comment this one out. Okay, cool. So we're going to try this now. I don't actually want to run the, and we're same thing. We're going to start it at 10, right? So OQR blew up, whatever. But this looks really good now. That thing blew up. We don't want that. Okay, cool. And I don't want to run that again. We just want to watch it. That thing blows up and it's stupid. This is the good one. So now check it out. Super smooth, super nice. And like I can basically now with this controller do anything I want. I can like set it up to start anywhere, like, and it's gonna just like, because right, I've like put bounds on the states in the controller that tell it like not to go outside where the linearization is good. So it's not going to be uber performant, right? Like if I did something fancier and more nonlinear, I could get more performance out of the thing. But this is going to be stable, safe, all the things you want, right? Okay. Anyone want to try anything else?
With respect to constraint, if you said like stay above the ground, because like in a sense like it doesn't know that it's falling.
Yeah. So that's a good question. We can try it. I actually would have to add the code then and to pick out those states. So it might take me a minute. Maybe we should do this after. But you can try it. Like there's actually a good chance it would, because it's going to try to enforce it now. And if you're kind of like, because of the feedback, it might actually do a better job than you might think. But yeah, this is a big problem in general, right? That like this like back to like guarantees on things, right? All of those guarantees are based on assumptions. Here, we're assuming that our linear model is good enough such that, so when I say it's guaranteed to be safe, because I put this like don't go through the floor constraint, that's modulo the model being accurate enough, right? So like, if I'm using an approximate model, maybe it doesn't hold up. It does hold up more often than you would think though, because the feedback magically kind of mops up a lot of the errors. So it might still be okay. But yeah, the bigger point I wanted to get, you could do that, right? It's a convex constraint. It's a half space, super easy. Definitely do it. In general, you'd probably want to do stuff like that. But in this case, yeah, the real answer here is bound the states, the delta thetas, so that it doesn't go too far away from the linearization point. And I didn't push this that hard. So this is like another kind of, we've actually done this on hardware. I can show you a video. You can push that really, really far. It turns out it doesn't break until you're like past 45 degrees. So you can push it out to like almost 90 degrees, and the linear model still holds up like surprisingly well.
Something like that, if you did want to, could you just linearize it around multiple points? And like if you want to go really far to this, like really quickly to the side, you just switch which linearization you're using.
So you absolutely can do stuff like that. There's a whole field this was hot in like the 80s and 90s. It's called gain scheduled control. It's this idea of using piecewise linear models. So you basically linearize the model around a bunch of set points in the state space, and then you switch between them online. You can absolutely do this, and you can prove various nice things about this using Lyapunov techniques. It's actually surprisingly closely related to ReLU policies. Guess what a ReLU network outputs? A ReLU network is a piecewise linear function. It's piecewise affine. So it turns out these ideas are extremely closely related. And this is one of the hand-wavy arguments that a lot of RL people use to like justify using ReLU networks, is that it's a piecewise affine policy. And that's exactly what people were doing 20, 30 years ago with these like gain schedule ideas and piecewise affine, models and policies and all that good stuff. So there's more connections there than you might expect. But yeah, like, so one thing we could try here real quick, because I can do it fast, is we can loosen up those bounds a little bit more. And we have time. We're basically done. So we got 3 minutes left. Let's make this like, I don't know, 0.5 or something, and see if we like push this a little bit more aggressively, what'll happen. But yeah, adding the height constraints easy. We could do that too. I can't actually read this, so I hope I put it in the right spot. And then we can try making this like super big, like to the point where it would, slam it, something like that. But yeah, it will work. Question is like how crazy it's going to look. Sure. That's going to do stupid things. Let's see what this looks like. Yeah. So, I mean, yeah, it's pretty good. So you can push these things. One of the other takeaways, there's a famous quote by Art Bryson of one of the most famous like optimal control books, Bryson and Ho. be wise, linearize. Like meta takeaway for the day, linear models are actually extremely powerful. You can do way more than you think and push them way harder than you might expect, which is why like so much of control theory is based on linear models. They actually work. They actually work in practice like amazingly well. Cool. I think that's it for today. We got, I'll show you a crazy video if you want to see this running on a quad rotor, like how hard you can push the linearization. Let me find it. Yeah.
We present Tiny MPC, a
Okay, check
high-speed,
this out.
low-memory footprint solver for model
Starting out at 90 degrees.
microcontrollers.
This is a single LTI model linearized.
Model-predictive control is a powerful tool for controlling robotic systems subject to complex constraints. It is computationally demanding.
Which is obviously
Many
not a
robotic
small angle of
platforms have
approximation.
limited
It's still fine.
And in general,
And
the
the
smaller
real
diameter
answer there is that having the
the
thrust
same
limits saves it
to
from
stabilize their
like
higher
completely
speed
blowing up.
dynamics. Any of
Anyway,
these
there you go.
designed around the premise of bringing model prediction.
Thanks, guys.